In the previous two problems, we've shown how we can use the first two laws of thermodynamics to understand how enthalpy and entropy of a substance vary with temperature. For phase changes, we can use the enthalpy and divide it by the temperature of the phase change to get the entropy associated with the phase change. The enthalpy of a phase change, delta RH, comes right from calorimetry because we have, again, that nice idea that if delta H for a process is going to be equal to Q when we're at constant pressure with no non-mechanical work. Again, since in general we have to add work non-mechanical, but if there's no non-mechanical work, we just have delta H is equal to Q. Then at constant pressure, similarly, we can do calorimetry versus temperature, measure the heat flow to determine Cp for the substance. Cp directly will give us delta H, and then we can get delta S from taking the Cp, dividing it by T, and integrating it in that fashion. The last point here, though, is that if I'm thinking about an actual chemical reaction, say water reacting with oxygen to make hydrogen peroxide, calorimetry experiments could give me delta RH or delta RU for this reaction by doing this either at constant pressure to get delta RH or in a bomb calorimeter, constant volume to get delta RU. But since these processes are not reversible, we're not going to be at equilibrium the whole time, we can't use them to determine delta RS for the reaction. So we're going to need another approach to get this delta RS for chemical reactions because our normal definition, remember, relies on having a reversible process, and we don't have a good reversible process necessarily for chemical reactions. But we have this nice process that can give us delta RS for chemical reactions indirectly if we use the third law of thermodynamics. So the third law connects our macroscopic definition of entropy back to our microscopic definition. S is Kb ln of W, where W is the total number of microstates. So if we go back to exam 1 and think about our energy diagram for, say, a particle of a gas or a solid, at absolute zero, what happens to the total number of microstates and the entropy of the substance? Again, if you think about this for a second, you should get a nice, clear answer. Okay, so remember at absolute zero, what has to happen is all of the particles end up in the ground state. The 1 here is sort of like the probability, right? I mean, whatever or 1 mole of particles, it doesn't really matter. Since every single particle is in the ground state, we have to have Waze is equal to 1. There's only one macrostate where all the particles can be in the ground state. And then as a result, S is Kb ln of W. ln of 1 is equal to 0. So we get 0 for our entropy. That gives us our third law. As the temperature approaches absolute zero, the entropy of a perfect crystal approaches 0. And that comes from this nice connection. Okay, this is less grand and dramatic than the first two laws of thermodynamics. Okay, we've got this perfect crystal in here. What's going on with that? The perfect crystal idea is that there are certain substances where they have some entropy left over at 0 Kelvin. If I have an energy diagram that looks like this, where there's 2 possible ground states, then at, the absolute zero here, each of these get an equal share of particles, and I have some leftover entropy at 0 Kelvin here. Each particle here actually has 2 choices, and what I have is that each particle has 2 ways, or 2 microstates. A whole mole of particles has ln 2 to the power of Na. Since each single particle has 2 microstates, so it's 2 times 2 times 2 times 2 times 2, Avogadro number of times. And then if I do that, I have S is equal to Kb ln of 2 to the Avogadro's number. S is equal to Kb Na ln of 2, which is R ln of 2. So again, for a substance like this where we have two possible ground states, we have some leftover entropy at 0. But most substances are this sort of perfect crystal, and so each particle has only one ground state, and we get 0 entropy at 0 Kelvin. Okay, one more key set of takeaways. So there is an absolute scale for entropy, unlike energy, because we can interpret entropy in terms of the total number of microstates. So it does make sense to compare the entropy of water to the entropy of gold to the entropy of any other substance. We can have that clear interpretation that if I'm comparing two entropies, I always can compare them. Unlike energy, where energy, we always have to have that reference point. I could define the energy of gold to be 0 or the energy of water. Since there's no chemical reaction converting them back and forth, there's no real way to compare. But for entropy, that's not the case. We can always interpret in terms of microstates. Now, for independent distinguishable particles, the microstates would look like this. The total microstates is the microstates per particle times how many to the power of how many particles I have. Again, if I had 3 particles and I have 4 ways each, then it would be 4 times 4 times 4, all the way back to and probabilities multiply. And so that's where this equation comes from, 4 times 4 to the times 4. That would be 4 to the 3. So what that looks like in general is that I take the microstates per particle to the power of how many particles I have, and that gets me the microstates for the whole system for independent distinguishable particles. Then we get this nice result if I can take this definition of entropy, plug in microstates per particle to the power of n. That n comes out front. If I have 1 mole of particles, I get the molar entropy is Kb times Na, ln of the microstates per particle, which is R times the ln of the microstates per particle. And again, we also have distinguishable here as a caveat here. If the particles are undistinguishable, we have to divide this by a factor to account for the particles being indistinguishable. Okay, so now if I have 2 different states, I can actually compare the microstates to a particle, assuming they're independent particles. And here, actually, it doesn't matter if they're distinguishable or not. If the particles are independent, if I subtract the entropy of each and then recombine these 2 terms to get R ln of WB over WA, I can say the change in entropy here is R ln Ways final over Ways initial, or Ways B over Ways A for some process. So if my delta S is a certain number of joules per mole Kelvin, I can interpret that directly into how many ways per particle are there if the particles are independent for the new versus the old state. Okay, so next, an example for our liquid water molecules. What would be the relative increase in microstates per particle going from 0 to 100 using the example we did before? Okay, so using the equation, we just need to rearrange it to solve for Ways final over Ways initial. First, divide both sides by R. Then to undo the natural logarithm, we take e to the both sides, and we get e to the delta S over R. And when we plug that in, we get, okay, then when we plug in, it's 23.55 going from 0 to 100. We get about a factor of 17 more microstates. So that says that all those different rotations going on in the water, there's now a factor of 17 more possible microstates, assuming they're independent. Not a great assumption because of the hydrogen bonding in water, but gives us an idea of that increased freedom of the water molecules as they go from 0 to 100, and therefore the increased entropy. Okay, the next thing going on here is that this third law now lets us determine delta Rs because we can think of this sort of cycle, even if we don't actually do reactions in this way, we can think about this, I don't know, sort of crazy looking cycle where a reaction A to B at a given temperature, we can't calculate delta RS directly here, but we can say, okay, I can use calorimetry to put A in a calorimeter, started at 0 Kelvin, warm it up to whatever temperature I'm interested in. Then I can use that calorimetry data to get the heat capacity, use the heat capacity and the enthalpy of any phase changes to get the entropy of substance A at room temperature, because at 0 Kelvin, I know that these substances both have zero entropy. Again, going from A to B at 0 Kelvin, if they're all perfect crystals, this is 0 joules per mole Kelvin at 0. So this, we're assuming, or if they're both perfect crystals, delta RS there is actually equal to 0. But either way, we can actually figure out the absolute entropy of A at this temperature. We can figure out the absolute entropy of B at this temperature. And then from these separate calorimetry experiments, get delta RS. So this is sort of the final missing piece. Again, because we can't do chemical reactions reversibly under most conditions, it was, before very, very difficult to get delta RS for a chemical reaction. But from these two separate calorimetry experiments, we now actually have a way to do it. Okay, this leads into the last thing we need to sort of go through our standard thermodynamic tables. Thermodynamic data tables that you've used in prior chemistry classes and that you now have available to you here tabulate the properties of solids, liquids, and gases at solids and liquids at 1 bar, so 1 bar of applied pressure. It turns out for solids and liquids, it doesn't really matter very much. There's, if you're at 1 bar of pressure versus 2 or 10 or in vacuum, not much difference to the properties of solids and liquids. But for gases, the actual pressure of the gas, and particularly its partial pressure, makes a huge difference. The partial pressure of any gas from prior chemistry or physics is the moles of that gas times RT over V for an ideal gas. Usually a good assumption. So again, we can say the partial pressure of gas X is that. Again, if I have 5 different gases, I can say the total pressure is the pressure of, say, gas 1 plus gas 2 plus gas 3, and so on and so forth. So for gases, we say that the standard state is a partial pressure of that gas of 1 bar of pressure. And again, this is going to depend a lot on the pressure, because we've seen before, if we do these isothermal processes, we get big changes in entropy when we compress or expand a gas. Similarly, in solution, the standard state is a concentration of 1 molar, which is 1 mole per liter of solution, or basically equivalently 1 molal, which is 1 mole of the substance per kilogram of solvent, and just happens to be a little bit easier to unit to work with sometimes. This standard state is where all of our thermodynamic data tables are tabulated, and it's denoted with a little circle. So S circle, or S naught, is the entropy at these standard state conditions. So at 1 bar of pressure for a gas, at 1 molar concentration for an aqueous species. Similarly, we can tabulate the delta R for a chemical reaction at those standard conditions, or the formation at standard conditions, etc. Again, the reason here, I've said it before, but we'll highlight it again, it's because the entropy of gases in aqueous species depends very strongly on the pressure concentration due to configurational entropy. The idea that if I go from having my gas in a volume V to now giving it more volume, let's say I double the available volume, and that basically doubles the waves or microstates for each of the particles, which causes this large increase in entropy because there's so many more available microstates in a larger volume. Okay, so we have the table of thermodynamic data. This is something you've done before, sort of more chemistry 120 review. We have the equation from the equation sheet. You have your thermodynamic data, determine delta RS and delta RH. All this data is at 25 degrees Celsius, 298, or if you want to be a little bit more specific, 298.15 Kelvin. That's where you're determining delta RS and delta RH from the given data. Okay, so first, delta RH, I have to do products minus reactants. The product is the gas, so negative 241.8 minus the reactant is the liquid, negative 285.8. That gets me 44 kilojoules per mole. The same thing goes for the entropy. And doing that again, products minus reactants, 188.8 minus 70 gives me 118.8 joules per mole Kelvin. Okay, then when we're thinking about the IMFs, the types of energy to determine what's going on here and check that these signs make sense, in the liquid, our picture of liquid water should be that we have hydrogen bonding going on between the negatively charged oxygen, partially charged hydrogen, very strong intermolecular forces in water because of those hydrogen bonds. Then when we go to the gas, there's now none of those hydrogen bonds. All these water molecules are far apart on average with none of those intermolecular interactions. Since we have to break this hydrogen bond to go from the liquid to the gas is going to be higher in energy. Again, we're breaking a bond to make the gas. That makes the gas higher in energy. Then thinking about the entropy is going to go back to all those different types of energy levels. In general, more entropy equals more closely spaced energy levels. So thinking about liquid water, that has rotations and vibrations. Everything has electronic energy, but I don't know. That's never really plays a major factor here. For H2O gas, we also add in translations because these gas molecules can now translate individually in a way they can't in the liquid phase. You remember, translational energy levels are the most closely spaced. So the fact that H2O gas has these translations means that it's going to have on net more closely spaced energy levels. So our overall picture then for water looks something like this. If I put all of this together on one of our cartoon energy level diagrams, and I've got H2O liquid and H2O gas, reactants and products, the liquid water is lower in energy. So that means the ground state of the liquid water has to be lower in energy than the ground state of the gas. Now, when I think about the more closely spaced energy levels, that's going to come down to the translations in H2O gas, making it have much more closely spaced levels. So adding that to our picture, we're going to have something that looks like this. Very closely spaced energy levels in the gas, more farther apart energy levels in the liquid. And that does match our picture here showing the signs of delta H and delta S. Delta H, again, mainly just related to this big difference in ground state energies. There's some effect from all these other energy levels, but mainly the ground state energies. Then delta S, again, when I think about the possible microstates, many possible microstates here for the gas because of the more closely spaced energy levels compared to for the liquid.